Now, how is it that we would know whether we've reached equilibrium or not? You know, in the previous example where we had a color change, maybe we can tell, if you're really good, when the color change stops, and we know that we've reached equilibrium then. However, most reactions, you know, our substances are usually either colorless or white or gray, and they don't really, you know, look like they've changed much. And so how can you tell if you've reached equilibrium? What you could do is you could calculate something called the equilibrium constant. At a given temperature, each reaction has a certain equilibrium constant, or a constant value for an equilibrium expression. Equilibrium constant, you know, in chemistry we use K for constant, and so you could call it just K. You could call it KEQ, EQ for equilibrium, so equilibrium constant. Or you could call it KC. C stands for concentration. So the constant in terms of concentration. Now, if you have a reaction, A plus B yields C plus D. Sorry, the arrows are in a weird spot there. Where capital letters are your substances, and the lowercase letters are your coefficients when you balance the chemical reaction. K is calculated as concentration of the products multiplied together divided by the concentration of the reactants multiplied together, and everything is raised to the power of its coefficient. So how do we calculate that if you actually have a chemical reaction? What you do is you wait until you've reached equilibrium for a known reaction, and then you take a sample of your mixture and you put it into a gas chromatography or a liquid chromatography machine or something like that, and then you measure what the concentrations are and you multiply them or divide them in this way to calculate K. Now, all of these concentrations are always in terms of molarity, and so they're moles per liter or molar. K is always constant under a set of conditions. So if your pressure and temperature and volume remain the same, then it's going to be a constant, and hence they call it the equilibrium constant. Now, what does K tell us? K tells us what happens at equilibrium in terms of the concentration of the reactants and the products. So if K is the number that's larger than 1, obviously K has to be a positive number because your concentrations can be negative. But if it's higher than 1 and you're doing products over reactants, that tells you that the concentration of the products is higher than the concentration of the reactants at equilibrium. And so in that case, when it's larger than 1, that means it's the one that looks like this, where your reactants are less than your products at equilibrium. If K is smaller than 1 and you are doing products over reactants, that means that at equilibrium it looks like this. There are your reactants, here are the products, and so that tells you that you have more reactants than you do products at equilibrium. So that's the significance of K. So the larger K is, the more product favored this reaction is. The more products are going to be at equilibrium. The lower K is, so if K is a really, really small number, that means reactants are favored for this reaction at equilibrium. Remember that when you write the equilibrium expression, that you only include aqueous ions, so aqueous solutions, and gaseous species. You never put liquids or solids in there. There is no concentration of a liquid or a solid. So let's write the equilibrium expression for these reactions. Let's start with the first one here. So H2 plus I2 yields 2HI. That was our example from earlier. So you would write, if you want the expression, that means they don't want you to calculate it, they just want the expression. So you say KQ is equal to the concentration of HI, it's your product, raised to the power of its coefficient, so raised to the second power, divided by concentration of your reactants, so H2 raised to the first power, so you don't have to write it in, times concentration of I2, again raised to the first power, so you don't have to write it in. So that's our equilibrium expression. Let's look at the next one. So if I want the equilibrium expression for this one, I'd say KQ is equal to concentration of my products. I only have one product, which is SO2, raised to the power of its coefficient, it's just raised to the first, divided by my reactants. Now I only include my O2 in my reactants. I do not include the S because it's a solid. So I only include gaseous and aqueous substance. So that's my KQ expression. Let's try the next one. So KQ, and again you can call it just K or KC. Any of these are equivalent. So concentration of my products, so concentration of Ag plus. Now make sure, because Ag plus here, that's an ion, not just solid silver. This is aqueous silver ion. You got to put the plus there. Times the concentration of my other product, Cl minus. Again, you need to include the charge there to indicate that it's an ion. And then divided by, well, my reactant is a solid, so I do not include it. So just divide by 1, or you don't have to put it in there. Let's try another one. KEQ is equal to concentration of my product, so SO3 raised to the power of its coefficient, so raised to the second power, divided by concentration of my reactants. Again, this is a solid, so I ignore it. I do put the oxygen though, so concentration of O2 raised to the power of its coefficient, so raised to the third power. So let's actually try a calculation here. Remember again that whenever we do calculations with Kc, that they need to be in terms of molarity, so moles per liter or mole. So this says determine K at 300 Celsius for the system. N2 plus 3H2 yields 2NH3, so you're making ammonia from hydrogen and nitrogen. And they tell us we have half a mole of nitrogen, 0.3 moles of hydrogen, and 0.18 moles of ammonia in a 2-liter container at equilibrium. So they're telling us that these are the concentrations at equilibrium, and we're trying to find K. In general, whenever you have an equilibrium reaction, or a reaction at equilibrium, the first thing usually that you want to write is your equilibrium expression. So before you calculate the number, just write the expression. So I'm going to write KEQ, or K, whatever you want to call it, is equal to the concentration of the product, so concentration of NH3 raised to the second power, divided by the concentration of N2 raised to the first power, times the concentration of H2 raised to the third power. Then, if you are trying to find the numerical value for K, which is, in this case, that's what we're looking for, then you plug in your values. Now, they give us moles, and they give us the volume, so we can figure out the molarity of each of my substances. So, concentration of N2 is equal to 0.5 moles divided by 2 liters, so 0.25 molar. Concentration of H2 is 0.3 moles divided by 2 liters, so 0.15 molar. And concentration of NH3 is 0.18 moles divided by 2 liters, so 0.090 molar. So then we plug in our values. So KQ is equal to concentration of the ammonia is 0.090 molar squared, divided by concentration of N2 is 0.25 molar. Concentration of H2 is 0.15 molar, but then that's cubed. Plug that into your calculator. You end up with 9.6, so that's our answer. Now, what does that 9.6 signify? Well, it's a higher number than 1, so that tells us that this reaction is product favored, meaning that there is more products at equilibrium than there are reactants. So you have at equilibrium, there are more products than reactants. Now, what is the significance of putting that 300 Celsius there? Why do they tell us that it's 300 Celsius? Well, we don't really use it, but that's because if you were to change the temperature, K would have changed. If you were to change the temperature, these numbers would have changed. And so whenever you read an equilibrium constant or you calculate an equilibrium constant, it's for that specific temperature. If you change the temperature, then that number is no longer constant. It actually changes. And in fact, the only thing that changes the equilibrium constant is temperature. All right, let's try a new one. So let's look at the next one. If K at 350 Celsius, again, they're just telling us the temperature just because K would change if you were to change the temperature. So it's this K at this temperature. We have HBr decomposing into H2 and Br2 gases. And they actually give us that K is 0.25. So they're giving us what the equilibrium constant is. This is a number lower than 1, so that tells us there are more reactants than there are products at equilibrium. Anyway, so they give us K, and they give us the equilibrium concentration for HBr is 0.04 molar. We want to find the concentration of hydrogen and bromine gases at equilibrium. So first step, since we're talking about equilibrium here, is write your KQ expression before you do anything else. So let's do that. KQ is equal to the concentration of the products, so H2, times the concentration of Br2, divided by the concentration of the reactants, so concentration of HBr squared. Next, let's try to see what we're solving for. We are trying to solve for the concentration of the H2 and the Br2. And we are given the value for KQ, and we're given the value for the HBr. Now, what do we know about the concentration of H2 and Br2? Well, we don't know what the value is, but we do know that they should be equal to each other. The reason they're equal to each other is because they're products and they're forming when you decompose the HBr. For every 2 HBr's that you decompose, you're going to form one H2 and one Br2. So these concentrations are always going to be the same because they're a 1-to-1 ratio and they're being formed. Initially you have 0 products, and as this decomposes, you're forming for every H2, you're forming one Br2 as well. So it's a 1-to-1 ratio, so you know that these two are equal to each other. Whenever you are trying to solve for concentrations or something like that and you don't know what they are, just say let them be equal to x. So I'm going to say let the concentration of H2 equal x. That means the concentration of Br2 is also going to be x because they're a 1-to-1. So now I'm going to plug in my values. So KEQ is equal to x times x divided by, they tell us HBr is 0.04 molar. And they also give us the value for KEQ. KQ is 0.250. So I know that x times x divided 0.04 is equal to 0.25. So that means x squared over 0.04 equals 0.25. If I multiply those two numbers, I'll get what x squared is equal to, and then I can take the square root. So then if you solve for x, get that x is equal to 0.02 mole, which is my concentration of H2 and my concentration of Br2. So that's my answer. All right, that's it for today. Hope you have a wonderful rest of your day.